Welcome to this talk. Almost good afternoon. Yes. So we are in an era where GPUs rule. This is why we need to pay attention to array programming on GPUs. And GPUs are fundamental to several aspects of computing that are all highly energy intensive. And of course, we know the toll they take on our purse. Coming to some of the more familiar GPUs, they have well-recognized entities such as CUDA cores and Tensor cores, delivering a certain level of performance and has a certain price point. The reason why I would like to mention some of these mundane details is to introduce some of the terminology, which is where this slide is going. Not only are the SIMT cores important, but also Tensor cores increasingly, because a lot of the computation happens on them, efficient machine learning training, and increasingly also HPC workloads are being shifted to Tensor cores. And they actually are occupying an increasing amount of silicon area, and there's a considerable interest in using them for HPC because of their potential to offer 8x performance boost if used correctly, if you feed the data without hiccups. This slide tends to introduce some of the terminology I'll be using. So either you write a CUDA C program with calculations such as here, a compiler takes over and produces PTEX code, which is lowered to SAS code. Or you might be interspersing matrix operations using these WMMA sync operations, which are small matrix multiplication operations. They turn to PTEX code, such as this, and they have their own corresponding SAS binaries. And these executions are carried out by warps. So if one of these operations, like fmul, is repeated across the threads in a warp, the entire small matrix multiply is done collectively by the help of all the threads, taking various row indices and corresponding column indices and multiplying. The reason that I introduced all this is that you will soon hear about binary instrumentation as what one of our main techniques is. And the long story short of why we need binary instrumentation is it is the honest reality. After all the optimizations are done, we get to see the effect of the actual execution that happens in hardware. And also because many of the libraries are closed source. So we really cannot understand what goes on unless we look at that level. There is nothing else to instrument. So for these reasons, or the tooling that I'll be mentioning will be referring to the PTEX, the SAS level rather. But coming to the main point of the talk, now that I've gotten some of the background away, energy drives decisions in this space. This is well known. So one of Bill Daly's talks, he repeated at Hot Chips in 2023 and also at other places. He points to the fact that arithmetic takes for inference half the energy. And the trend at least is clear that math is increasingly where we spend a lot of energy. So we have to do something about that to rein in because of obvious reasons. So this actually requires us to move fewer bits. So what do? So we either trade off accuracy or dynamic range based on the number system we select. And the kind of hardware is also not uniform. Many hardware companies, custom hardware companies are gone out of business, and we get hardware from AI vendors. So this is a challenge that is going to be faced by the larger community outside machine learning, which is where we are interested in. Some of our work actually refers to, in the mission of helping DOE labs such as Lawrence Livermore Lab, which is our collaborator, trying to move linear solvers to run on these kind of Tensor cores and strange hardware. So number systems essentially are the trade-off device, you can say, which helps trade off energy and also bugs, meaning the inconveniences of using inadequate representation. So if you take a look at what goes on in this area, this is a quick snapshot of the various number systems that exist. All the number formats written here. So if just let's look at BF16 versus FP32, which are 16-bit and 32-bit representations. Here you have the same largest normal number, which is the same dynamic range. But in terms of the amount of unit round off you get or the error you get, it is 16 orders of magnitude higher. So this is one aspect of how we can make trade-offs by not having enough accuracy but having the same dynamic range. So the kind of question to ask in such a setting would be, if you actually run some HPC code with that setting, you will probably not run out of range, but you will have really bad error. One can actually plug in these for typical values and see how bad it gets. Or if you can use other formats which are also 16-bit, you quickly run out of range. So I think this is the real game we need to play. I'm not mentioning other esoteric formats here, where you can use for forward one set of representation, and for the reverse gradient propagation use something different. Lots of things are happening in this area. So number systems is the playground in which we need to play and win. So how shall we do it as a programming languages community? What tools do we need? And can we all join to create some of these tools? This is where the talk is going. So I think the takeaway by so far is that GPU variety is pretty large, and debugging tools have not kept up, and the specs don't exist. This is another aspect of it. None of this is actually given to us, so we had to discover what these hardware units actually do. And also having many specs is also not good, because having a lot of specs means that you really do not know how we can move code from one platform to the other. So let's focus on three types of bugs. Bugs in the sense of issues we had to deal with, where we pay the price in terms of software correctness. So basically, the first one is of exceptions. The second is that of ill-specified hardware, and the third is that of lack of formal specification and managing their excess. So let's take a quick look at exceptions and what they mean. So it is very easy to see that even when you do a dot product, you run out of range. Even for FP32, 1.9 10 to 19 runs out of range. So it is very easy to get infinity values even for the familiar FP32, and less values are needed. For FP16, you run out of 16 square is out. Infinity and nans are the most serious. We'll not look at the other floating point exception types. And things like that a C programmer write like this are incorrect in floating point. It's easy to see why. If you plug in x equal to nan, the comparison turns to false. That's IEEE defined. So you get y, which is the answer, which could be 42. And if you swap x and y, where you feed the nan to y, the answer is nan. So even max is not commutative at this point. And the reality is that in a system where you have exceptions occurring, exceptions are generated, they propagate through the code, and sometimes they vanish. But by then the damage would have been done, and this is the real problem we need to be aware of. Classical CPU era solutions do not work. CPUs are used to trap, and that's not possible with GPUs. They largely just report the exception as an exceptional value by encoding the floating point exponent field or the mantissa field. That's the story for NVIDIA. For AMD, they have a little bit of an indication of something happened in this kernel call. Nothing much can be put to use even with that much effort, that much announcement. So let us say that we just need to deal with the exceptions as a value, not as an event. So what are the mechanisms to actually see what goes on and whether it even happens? So we could take a look at what happens in very well used libraries such as PyTorch. And it's clear that, and I'll basically refer to as these aspects. So basically there are various layer types, and they have anomaly detection mechanisms and scaling steps. So there isn't a paper that I have seen that summarizes all this. This is anecdotal, and of course this is a GPT printout, let me be honest. But essentially these kinds of mechanisms are known to exist, and anyone who actually works with optimizing the machine learning compiler part itself will see the kind of issues in this area. And even the mechanisms that they provide to deal with some of these contingencies do not work, and they come with a high cost. So for instance, some of the familiar methods are clamp before the trouble occurs, gradient clipping, loss scaling, replacing infinities. Maybe machine learning systems can get away with this, even though the price that they extract is very clear. I'll mention some numbers. But what is the approach that we should take, given that this is the same hardware type that is to be supporting non-machine learning computations like HPC? This is the point to ponder. So just to call out one of these, there is a exception detection everywhere by autograd detect anomaly. It produces a 3x slowdown, so we don't want to be doing things like that. With HPC, what we have observed in a paper in 2023 in HPDC is when we deployed a binary instrumentation tool that we developed at the SAS level and applied to several benchmarks that are getting ported to run on GPU. This is a summary of over 256 examples, small to medium to large. Some of the cases we had sources available, some of the cases we did not know what was going on because it was not code that we wrote, and in some cases we can say the exceptions do not matter. But largely the exceptions did occur, and in one case the solution itself was polluted by nans. And then we had to ask a numerical scientist saying, what do we do? They said there's an API in this library called boost diagonal, apply it, and sure enough the exception vanished. That allows the numerical scientist to get to the next stage in their experimental pipeline, but this is not a long-term viable solution that we would agree. So what is the standard that we should aspire to? This is something that the PL community has to actually articulate. One of the simpler definitions that I have seen with which Jim Demel has put out is that of sound or consistent exception handling, and he has applied it to construct BLAS routines. So he actually shows several BLAS primitives, and what is required is that the exceptions are either correctly handled in the code or at least manifest at the output of the function. And without that, we cannot really work with it. If it silently disappears inside, that is not a well-designed module. Of course, if you look at Jim Demel's report, it actually becomes clear how much the code increases in terms of incorporating this measure of proper exception handling. They have a really nice paper on how to spoof exception values and find this. It's a very neat technique, but it doesn't seem to scale. It perhaps would not scale. I haven't tried it, but my mental math says it is not for large piece of code like we are talking about. So I think the gist of this talk is to see how the tooling looks like and what the dangers are. And I'm hoping to show you where we are in at least in the exception land, and we'll come to the other two aspects of bugs that I mentioned earlier. So the instrumenter that we have built, this is the old tool, GPU-FPX, is available. So if you grab that URL, it's also available on my homepage. Is able to find exceptions on SIMT cores. So even building this tool required us to understand what the SAS instructions mean, where the actual implied operands are, where the results are delivered. None of this is known. Sometimes there is a register mentioned, but the next register is also implied, things like that. Nixnan is the name that we are hoping to impart for the next tool. Sorry, question? No, okay. Yeah, so this is a tool that we are building for Tensor Cores, where the task is that of grabbing exceptions from every lane and then packing them into a unified word. That's also available. It is a new tool that we need to put to use, so I invite you to try it. So how does a tool like this use in terms of in terms of usage? It's pretty simple. So if you look at the left hand side, I'm training a simple n-gram DFA that the GPT that Karpathy designed is learning. So it's learning the language as an n-gram state machine. So the training finishes, and it finishes in about 2 seconds. What happens is to use the tool, all you just to do is a LD preload of the analyzer and then the same command. So at that point, the instrumenter is ready, armed, in action. Whenever a kernel launches, it looks for floating point instructions that generate exceptions, and then it reports a summary of the exceptions. So in fact, you can kind of X-ray down the stack and start seeing which kernels are getting visited, what exceptions they are reporting. And the net effect is that information plus slowdown. In this case, it finishes in 4 minutes. So that is the slowdown you can expect. This is a highly intrusive process, but it works in pretty much all the cases. Does it do consistent exception handling? The answer is no. A lot of exceptions happen. None of them seem to be in the final answer, not in the loss function. Of course, it happens. When it happens, people actually notice and they do something about it. So you can even do a casual search of PyTorch, AutoGrad, exceptions, NaN, and you get thousands and thousands of hits. So the community is paying the price. It's clear. The kind of reports we get like this are somewhat useful, and I'm not making any pretense that this is the ultimate stopping point. We all need to work towards it. But as a hilarious experiment, I took these scripts that were produced and uploaded to GPT. And it seemed to understand that this exception can be interpreted. And it actually told me that these are the kernels in the PyTorch that are involved. And it even gave me a severity rating. Take it with a lot of salt. But the real news is that if you have a captive agent that goes with the framework that you're building, maybe it will learn over time the kind of traces and the bug fixes that you manually did. In any case, there is a real need to triage and attribute severity level to these exceptions. Not all exceptions matter, but some of them do matter. This is where we need to be as a community to understand and have a systematic way to do it. One of the examples I'll tell you is an open issue on GitHub that my student looked at. And it was a simple recurrence unit where the issue was not fixed. So the relevant piece of code looks like this. It's a piece of Python code. So we applied the instrumenter, and it actually does a flow analysis through the instructions, saying where are the exceptions getting sourced, where do they conduct, where do they disappear. And in this example, we learned that the exceptions were present very early in the tracing. And with some head scratching that is inevitable, we knew that the exceptions were soared by the fact that the data was not properly initialized. The person allocated a tensor thinking that the memory will get cleared, but that doesn't happen. So if you change it to torch rand like that, the exception goes away. So at least there's some value in understanding that it might be a mistake that you made in your code. Basically, that is about what I can say. So there are 4 or 5 experiments I have presented in the paper, 2 involving lossy data compressors, and all of them have this possibility of generating exceptions, and the tool is able to at least tell you what kernels are involved, and this is the direction that we have started, but I don't think the community is fully engaged in tracing. There are LLVM level tracing tools, but that can probably help at a level where LLVM is available. Changing gears, we are now going to briefly spend some time in terms of lack of specifications and what do we do with too many specifications. That will be a few minutes spent on each of these topics. Tensor core operations are able to support operations of this kind, d equal to a times b plus c. The kind of math involved and the rounding rules are being discovered. There is a set of papers by Fassi and Mantas, Mikaitis, Nicholas Hayam, the late Nicholas Hayam. They found out that the FMA operations are applied blockwise. So if you have a dot product, you chunk it up into size of 4 or size of 8, and for each chunk of 4, the dot products, the times and plus have one rounding error, so like that. So between blocks, there is no FMA effect. So the block width actually becomes apparent when you actually use it, and it can be dramatically shown by creating a simple calculation like d equal to c minus ab, which occurs in many linear algebra codes. And we looked at the intended math and filled all these matrices C, A, and B with the values that we made, my student made. And we could make these 3 units and the CPU produce 0 as the final answer on an 8K by 8K matrix. On an MI 100, we made it produce 255, and on H100, we made it produce 191. So the kind of answers, these little errors do add up, and 8K by 8K is not large. So if you get numerical variability of this order, it's not in the last third fractional digit, it is in the third significant digit that they are showing, which is far higher. So this is the kind of danger we will face if you don't have a calibration for the hardware. And there are tests that we have devised to discover specifications. So this is a test that runs through Tensor Core and finds out the block FMA width, which is not known before. And we have published these tests also. This was in a paper last year. So the kind of specifications we have discovered are of this kind. So if you look at precisions and GPU types, we have discovered variations in terms of where the subnormals are handled or not. We have discovered how many extra bits are kept in the floating point rounding, because for round to nearest, you need 3 extra bits below the LSB of the mantissa, but that's not present always. So you cannot expect certain rounding modes. Then the block of FMA width changes. So I think the fact that the calibration is not there is a big worry. That's the news here. And let's now look at further problems that the lack of specification or even having too many specifications might create. It is going to affect our ability to understand devices, auto-generate code, verify auto-generated code. All these things are going to be affected by either a lack of specifications or lack of specifications. So for instance, this is a piece of code that GPT generated to find the max element of a matrix. It uses shuffle sync and highly optimized instructions, and this code seems correct, and the human scrutiny told us it is correct. But in another instance, Claude generated a piece of code like this, where it was scheduling work for an inactive thread in a warp. So that is obviously buggy. So even for short, pithy, fast codes like this, if we have an SMT specification maybe for the instructions, perhaps we can hope to verify some of these codes that will inevitably get used by people. If we don't give them the tooling, they will have possibility of bugs in their system. This is a paper that a collaboration between Rochester and Utah resulted in this paper. We have an SMT model for 3 generations of Tensor Cores, and the student won a best paper. So this is worth looking at. This is where the surfeit of specifications will start affecting. In our current work, we are actually taking linear solvers and porting them to run on strange hardware. And iterative refinement is one of the modalities where low precision is going to be used, low precision hardware is going to be used. So we'll core solve the X equal to B. This is a highly published, well known in the numerical community. Compute the residual and then solve for the correction term, update the solution. So this is kind of iterative refinement scheme, and various other schemes are proposed. And the question now becomes, what precision choices would you make for all these steps, and under what condition would such a linear solver deliver results reliably? This is where the HPC community has to head anyway. So I'm done. The challenges are, we really have coming to us all the high performance hardware without too much tooling. The community is also largely unknown to us. We hope we can form a community around workshops like this. We are offering some tools that you please should try and help us improve. Let us make the tooling in this area strong, and also start building formal specs. If we have a library of specs that we can build, we can probably share, and the community will at least be able to match up to the, I mean, at some point the communities, companies have to cave in and provide us more, but I don't know when that is happening. And last but not least, we really need to know how to emulate when there is a variety of hardware, how do we port applications across without surprises. I think that pretty much summarizes what I had to deliver today. So thank you.
Thank you very much. Thank you. So we started a little bit late, so maybe we can take one question.
There's one question there.
Oh, awesome. Thank you. I guess in terms of what kind of spec do you want? So I think one, I'm in NVIDIA now. Yep. And I think one of the questions that we've been doing specification stuff around the Tensor Core,
yep,
and how do we communicate it is maybe the big open question to me, because some amount of variation per generation will happen.
Yes.
So like, we could go the extreme way of something super formal for every single release and try to get it really precise.
Yep.
There will still be bugs, et cetera. But then also, what is kind of the bounds is like, do you want a guarantee that is forward compatible or future? So I don't know, but that would be a useful thing we can talk about offline as well, but if there's something in your mind.
I think this is a wonderful topic. I would say one could look at the variations that are possible. So multi-term adders exist, rounding modes exist, several combinations exist in terms of which exceptions are reported, which subnormal types are handled. Maybe start putting cocktails of these and say for this cocktail, this is what one can expect. Maybe one has to make it generic and then bind to the actual hardware as and when occasion demands. And Tensor Cores are a fast-moving area of NVIDIA's landscape because of the obvious reasons. So concurrency is a big deal which we have sidestepped. So I think both have to play out very well. So yeah. I'm available later, but I hope the basic message is clear. Thank you so much. Yeah.
Okay, let's thank the speaker again.